So now, girls, we're going to look at motion in terms of forces. We're going to link motion to Newton's second law. So first of all, a little bit of theory. This is on your handout. Say you have any particle, and I'm going to just for argument's sake here, or just to make it a bit more straightforward here, assume this particle is falling vertically. So it's moving through the air in a downward motion, so its acceleration is acting down. Look at the forces that are acting on it. Obviously it has a weight force which is acting down, and we're going to say it has a resistance as well. So there's going to be air resistance acting, and the resistance of course will act opposite the direction of motion. The air resistance is often given the expression m times kv squared. So here you go, you have an unknown in there which you'll probably have to find a value of as you go through it. Now, if you look at the forces acting on that particle, it's falling downwards. So what are the F nets? The F nets on that particle, because it's moving down, is mg minus r, which of course is mg minus mkv squared. Now, I know I can apply now these forces, link them to a motion if I use Newton's second law. So Newton's second law says that the F nets are equal to ma, which means that mg minus mkv squared is equal to ma. So g minus kv squared is equal to a. So that's a very useful starting equation that we often have to get, and then we can continue through and solve, of course, for a velocity or a time or a distance using the usual substitutions for acceleration. Now let's look at again a particle. This time we'll look at the forces on it. Obviously that weight force always acts down. Let's supposing it's being thrown up this time, or it's moving in an upward direction, a rocket or something. And of course there is air resistance again. Air resistance will be opposite to the direction of motion. So in this case, the air resistance will be acting in a downwards direction. And again, if I express this r as mkv squared, let's write a force equation for this. So what are the net forces acting on this particle? It's moving upwards. So no force is taken upwards, but these two are acting against the motion. So it's minus mg minus mkv squared. And then if I want to link that force into a motion equation, I'm going to use Newton's second law. And this is going to become F nets are equal to ma minus mg equals minus mkv squared is equal to ma. So minus g minus kv squared is equal to a. Okay, so I just have to decide which way the particle is moving and then work from there. Now, bearing, and obviously, look, there's a k in there, so you're going to have to probably find that k's as you go along through a question. I'm going to start with 2012, 10b, because that gives us a nice little, more or less straightforward one to start with. Now, this time the particle, it isn't moving vertically, it's moving horizontally. So, I'm looking at part B, it says, a particle is fired horizontally through a block of resistive gel. The resistance to motion is mkv squared, where v is the speed. The particle enters the gel at a speed of 1,000 meters per second, and after 1/100 seconds, it exits the gel at a speed of 10. So you've got to show that k is 99/10, is the first part of the question. So let's do that first. Right, so we have this particle, there's the gel, the particle enters the gel and it's moving in this direction through the gel. However, of course, there's a resistance to motion. The resistance to motion will act in the opposite direction, r. The other force that's acting on that gel, of course, is its weight force, which is acting down. But this force doesn't come into play because we're only interested in the forces that are acting in the direction of motion. And the direction of motion is horizontally, that way. Okay, so let's look at this particle. It tells me that this particle enters this gel with a speed of 1,000 meters per second. At a time 0, and after 1/100 seconds it exits the gel at a speed of 10. So they're my limits. Okay, so let's find k. We know the limits. let's find an equation. So the F nets, what are the forces acting on this particle? There's only an resistance force, which I'm told in the question is mkv squared. So the F net is just minus R. And by Newton's second law, the minus R is equal to ma. So this is going to be minus mkv squared is equal to ma. So minus kv squared is equal to A. I've got V and T in my limits, so I'll change this A to dv dt. So minus kv squared is equal to dv dt. Separate the variables. This will become minus k times dt is equal to 1 over v squared dv. I'll bring this up. Minus k dt is equal to v to the minus 2 dv. I'll put in my limits. So the limits for the t's are going from 0 to 1 over 100. And for v, they're going from 1000 to 10. Okay, so let's integrate this side here. This becomes minus kt is equal to, when I integrate the right hand side here, it becomes minus 1 over v. My limits, remember, as I said, they're going from 0 to 1 over 100. This is going from 1000 to 10. So when I put in the limits here, minus k 0 minus 1 over 100 is equal to minus 1 over, and I'll take that minus outside, so minus 1 over 1000 minus 1 over 10. So this will become 1 over 100 times k is equal to, when I subtract this, 1 over 1000 minus 1 over 10, it becomes minus 99 over 100. And I have a minus outside as well. So that's going to be 99 over 100, which means that, 99 over 10. What am I talking about? 99 over 1000 when I subtract that. Okay, so k is equal to 100 times 99 over 1000, which of course is 99 over 10. So I've done the first part. So second part of that question, so we found the value of k. It says use the fact that, this expression, or otherwise to show the length of the block of gel is 10 over 99 by the ln of 100. So we're looking for the length of the block of gel. Now I'm going to use the or otherwise expression here. Ignore that. Okay, so let's go back to what we know. We know that A is equal to minus kv squared. So that was our starting equation. Now we had this particle entered the gel with a speed of 1000, left with a speed of 10. We know that the time it took was 1 over 100 seconds. And now we're looking for the length of the gel, so the S, the length of the block of gel. So it entered it at the start of the gel and it finished it after a distance S. So find the length of the block of gel, find S. This is my starting equation. I use this to give me K, so now I'm going to use V and S so that I can get this fella in here. So to get S in, this is going to become V times dV ds is equal to minus kV squared. I'll separate those variables and this will become minus 1 over V dV is equal to minus K ds. I'll integrate both sides. I'll take that K out because it's a constant. The V goes, remember, from 1000 down to 10, and the S is going from 0 to S. So this will become, when I integrate this, it becomes the ln of V. This becomes minus Ks, and I'm using again limits, 0 to S and 1000 down to 10. So this will become the ln of 1000 minus the ln of 10 is equal to minus K times 0 minus S when I put those limits in. This, of course, will be the ln of 1000 over the ln of 10. So that will become the ln of 100 is equal to k times s. So k, I know from the first part of the equation, is 99 over 100. So this is the ln of 100 is equal to, or 99 over 10k wasn't it? Is times s. So s is equal to 10 over 99 by the ln of 100. And that's my distance, and that's of course in metres.